It will be about strategic fire sales and price-mediated contagion in the banking system.
Thank you, Carol. First, I'd like to thank Jorge, of course, for organizing the conference. Always great to be back in Rio, or in Búzios this time, even better. And happy birthday to Bruno, once again. So I'm going to talk about a joint paper with Jan Brouwezek, who's a colleague of mine at IÉSEG. So it's going to deal with strategic fire sales and contagion in the banking system. And so that's what the contagion that I'm going to focus about is what we call price-mediated contagion. But before going into detail, just let me give you a bit of motivation about this topic, because it's a very math-financed conference, and maybe everyone is not aware of the kinds of concepts that I'm going to talk about. So a bit of introduction about the work that we've done with Jan and also with Rama during my PhD. So the starting point was the observation of financial crises over the last decades. And one thing that was very striking was how financial institutions themselves played a very large role in propagating shocks in the market, right? So you had one shock in the market, and because financial institutions reacted to those shocks, they made those initial losses much bigger. And we had one of the best examples is during the 2007-2008 subprime crisis, where you had this shock to the subprime mortgage class, which is relatively to other asset classes relatively small, right? Which led to gigantic losses for all equity markets and lots of other markets, and huge losses for lots of investors around the world, right? So you had a shock which is relatively small to the subprimes, which propagated to lots of other asset classes and lots of financial institutions. So this is contagion, right? It comes from one shock and it goes to other assets, to other financial institutions. And when we talk about contagion in financial markets, there are essentially, so once again, to simplify stuff, there are two types of contagion. So direct, what we call direct contagion, and of course, indirect contagion. So what's direct contagion? Well, direct contagion is actually the most intuitive form of contagion that we would imagine in a financial market. It's a contagion which is due to contractual links between financial institutions. So for example, I borrowed money from a bank. If I go bankrupt, the bank is going to undergo losses, right? That's direct contagion because I had a debt contract. Same thing if I write an over-the-counter derivatives contract with another institution which was not properly collateralized, for example. If I go default, the other institution is going to fail because we had this direct connection, right? So this is the intuitive contagion mechanism that we have in mind when we talk about contagion in financial markets. And it's actually been modeled by academics for a long time using network theory, right? So I remember the first time I came in Rio, I saw a talk by Hamed Amini and also Andrea Minka on that topic. It's been tackled, of course, much before those guys, right? And it's also been tackled by regulators in the proper way because it's kind of the form of contagion that people would think about when we want to tackle contagion in financial markets. So I'm not going to talk about that in this talk because it's something that's been dealt in the literature for a long time. What I'm going to talk about is a more subtle form of contagion, which is what we call indirect contagion. So what's indirect contagion? Indirect contagion is actually a form of contagion which occurs through prices, and due to the fact that in some extreme cases, large financial institutions may need to sell some of their assets, and by selling assets, they're going to make those prices decrease, and they're going to impact all other institutions holding those assets, and so generate losses for them. And what's remarkable is that this contagion does not require any contractual link between the financial institutions. It's because institutions hold the same type of assets that there will be a channel for contagion. So you have one big institution which, for a reason or another, has to sell some asset. It's going to do that in the market, impact the prices of its asset, and actually impact all other institutions which hold the same assets. Right? So this is why we call this contagion indirect, because you don't need direct contractual link, or also price-mediated contagion. That's actually the title of the paper. So price-mediated contagion, because it goes through prices. Right? It's more subtle because people would not think of that as the first channel of contagion in for example, in a crisis, but there were many empirical studies which showed that indirect contagion and direct contagion actually played a very similar role and reinforcing role during financial crisis. So that's what I want to focus about. And usually when a financial institution sells assets in a hurry, right, it's what we call in financial literature fire sales, which are sales of assets which are kind of forced due to an exogenous constraint, capital constraint, liquidity constraint, something like that I'm going to detail for banks afterwards. And so the term is fire sale. So one of the characteristics of fire sales is that, well, usually when you do that, you don't have time to implement a proper liquidation scheme that would minimize the impact on prices. You have another kind of urgency to sell assets and to raise cash, and so the impact will be actually magnified on prices, and so on all other actors holding the same assets. So so one of the origins for fire sales for banks, for example, because that's what's going to generate this indirect contagion, is actually, and a bit ironically, it's the capital requirements themselves. So if you look at the banking system, it's highly regulated, of course, and all those successive Basel regulations have focused on making sure that each bank has enough capital compared to the size of its activities or size and riskiness of the activities. So in terms of regulation, it's translated into making sure that the risk-based capital ratio, so capital divided by risk-weighted assets, is larger than a certain threshold, like let's say 8%. So actually there are various thresholds in the Basel regulation, depending on the quality of capital that you put at the numerator. So I take this one as a reference. But what happens? Each bank has to verify this kind of relationship, right? So capital divided by risk-weighted asset larger than a certain threshold. But when a bank undergoes a shock, what is going to absorb the shock, the loss, is typically the total capital, so the numerator, right? And this is mechanically going to decrease the capital ratio of the bank. So what's happening is that if the shock is large enough, the bank may be left in a situation where its capital ratio is below the 8%, so it's not complying with what the regulator asks the bank to do, right? And then the bank has actually two choices, right? It has to bring back the capital ratio above 8%. And when you want to bring back a capital ratio above a certain value, you have two choices. Either, well, it's a ratio, right? So either you increase the numerator, so you issue new shares, right? Or you decrease the denominator, so you sell assets. Or you move from risky assets to non-risky assets. In general, in practice, it's pretty expensive for a bank to sell new shares, especially after a shock, because of the cost of issuing new shares, also of dilution of previous investors, et cetera, right? So what banks are going to tend to do is that after a shock, in order to comply with regulatory capital requirements, they're going to engage in fire sales, so try to sell assets in order to bring back the capital ratio above the 8%, right? And that's pretty ironical because it's the regulator's rule itself which is generating this behavior, right? But the regulator has to put some kind of an insurance that the capital of the bank is large enough. So that's something which is actually known by the regulators themselves, by the academics also. There's a lot of studies which have been describing this fact. So I've listed a few citations of some studies. So let me focus on this first one, which was of the Squam Lake report after the subprime crisis, which states that because of the mark-to-market accounting fire sales by some firms, that may force others to liquidate positions to satisfy capital requirements, you see? And in the end, when everyone engages in fire sales, which is actually the case when everyone is hit by the same shock, so typically subprime mortgages which were held by lots of financial institutions during the subprime crisis, well, the successive sales can magnify the original temporary price drop and force more sales. Right? So there's a clear instability mechanism here. And what's interesting is that this instability is first through the prices of financial assets in the market. Right? So the goal of this work is actually to provide a very simple framework. So you'll see that it's not a super sophisticated framework. It's on purpose, it's very simple and stylized framework to enable to capture this price-mediated contagion. So we're going to focus in the banking system, and we're going to look at a common shock which affects all the banks at the same time, right? And we'll study the equilibrium between banks and show how to calibrate the model to publicly available data. Right? So there's a lot of literature on the topic. It's pretty recent, actually, because this was this trend of literature became much more intense since the subprime crisis. One of the seminal papers, so there's a lot, if you read the paper, everything is cited properly, right? So in the interest of time, I'm just going to talk about the seminal paper that motivated our work, which is the Greenwood-Landier-Tesmar paper, who did the same kind of study for the European banks, so following the European stress tests, right? But in a leverage context, so not risk-based capital ratio context, and in a context where banks would react to a price shock, not taking into account the reaction of other banks. So what we're going to do here in this framework that we're going to develop is to actually look at a risk-based capital ratio, which is what the regulator is looking at first, and also look at the reaction of banks, not only to a price that moves, but also to the sales of other banks. So that's why we call the fire sales strategic fire sales. It's because banks' reactions to a shock is going to be determined not only by the shock, the size of the shock, but also by the reaction of other banks to the shock, right? So it's becoming strategic. Okay? So what's the framework? The framework is very simple. So you look at a set of banks, so P banks, that can invest in a very simple manner. Either they have cash or they have risky assets, right? So we here on purpose, and I'll come back on that point in a few slides, we look at a framework with one single risky asset. So VI is the amount in cash, right? So cash is, for the bank, is the non-risky asset, right? And QI is the value in dollars of the risky assets. So PT is like the price of 1 unit of the risky asset, and QI is the number of units held by bank I of this risky asset, right? You can think of PT as an ETF held, which would be held by all the banks, right? And which is the common risky asset that they all hold, right? So QI is actually the number of units, the number of shares of this asset that they hold. So some banks may hold a lot, so large QI. Some banks may hold less, so lower QI, right? So that's for the asset side, right? You have cash, you have risky assets. For the liability side, so once again, very simple, you have some debt, so typically deposits or debt securities, which we assume here a constant. So DI is the debt of asset I, of institution I, and the rest, which is the difference between the assets and the debt, is the equity, right? So that's the basic balance sheet that we would have, right? Asset side is cash, risky asset. Liability side is debt and equity, right? So let's come back to this assumption of one single risky asset. Of course, in practice, it's not true, right? Banks hold hundreds and hundreds of assets, so at least more than one, right? And so one should try to understand why we do that. Well, first, it's more convenient in terms of math, right? You would guess. But it's still possible to extend that to multiple assets, and maybe we can discuss that in the end. But from a stress testing perspective, actually, we believe it's interesting to look at one single risky asset, because it would mean actually that the portfolios of the banks are highly correlated, and actually in our case, the risky part of the portfolios of each bank are correlated to one, right? Which is not true in practice, but which is good in terms of stress testing. It's kind of the worst scenario. Also, there are some theoretical, empirical studies which have been done which show that in times of crisis, the portfolios of banks tend to be highly correlated, right? So that's kind of the motivation for this, one of the motivations for using a single risky asset setting, right? Another motivation is that it's very easy to calibrate our model to public data. And that's one of the force of the strength of the approach that we are proposing here, contrary to the stress tests which are proposed by the regulators or lots of very sophisticated studies which have been proposed by academics, right, which were very interesting, we here need only a very few data to calibrate the model and have some order of magnitude, at least, of the magnitude of price-mediated contagion in the market. So kind of a measure of the fragility of the market to this kind of contagion. Okay? All right, so that's for this risky asset assumption. One other assumption is that this risky asset is not issued by a bank, so that we really take into account a framework for pure price-mediated contagion, in the sense that the only way that a bank can impact another bank in our setting, right, once again, that's the model, is through this price of this risky asset PT, right? So bank 1 can impact bank 2 only by selling some of the risky assets that bank 2 is holding, okay? All right, so we're doing everything on a risk-weighted framework. So the risk-weighted assets is just denoted alpha I, so risk weight, times the size of the risky asset, PT, times QI. Okay? So alpha I is actually the risk weight calculated by bank I for this risky asset PT, right? So it can actually depend on each bank, although it's the calculation of the risk weight for one given asset. It's because under the advanced internal rating-based approach, banks are allowed to use internal models to calculate risk weights. So they may actually end up with different risk weights for the same assets. So here we reproduce this fact of alpha I. Right, so if we look at the capital ratio, it's very simple. You have the equity, so total assets minus the debt divided by alpha I, so risk weight, divided times the size of risky assets. So that's the risk-weighted assets here. And we assume that in the beginning, all banks are complying with the capital requirement. So that means that they are above theta mean, so above 8%, for example, which is the Basel standard. And then we input a shock in this market. So this risky asset, the price was PT, it decreases to PT times 1 minus delta. So delta is the decrease in percentage, so maybe 1%, 2%, 5%, 10% would be a very big shock. And actually, mechanically, we see that the capital ratio of each bank is going to decrease. Why is it going to decrease? It's because this shock is going to be absorbed by the capital, which is at the numerator of the capital ratio. And the bank may face different scenarios, different situations, depending on the size of each of the shock. So, for example, if the shock, so you can quantify two thresholds, so delta cell and delta fail. If the shock delta is below delta cell, that means that the bank I is able to absorb the shock, but also after the shock, the capital ratio is above 8%. So actually, the bank doesn't need to do anything, right? It's still alive, and the capital ratio is above 8%, so you still comply with what the regulator asks you to do. On the contrary, if the shock is above delta fail, the bank is insolvent. So it's not even able to absorb the shock. The shock was so large that the bank's equity is fully wiped out, and actually the bank in our framework will be liquidated. Interesting case is when the shock is between delta cell, which is computed here, and delta fail. In this case, the bank is able to absorb the shock. So it had enough equity to stay alive, but after the shock, the bank's capital ratio is below 8%. And so that's not good for the regulator, because the regulator asks that the bank's capital ratio should be at all times above 8%. So as I was telling you, in our framework, we're going to assume that the only possibility for a bank that is not complying with regulatory capital ratio to comply again with capital ratio is to sell assets. Right? You could imagine a scenario where the bank issues equity, and we could incorporate that here, but this is not likely in practice, and also it would just like complicate a little bit the math, but not give that much insight, right? So here we assume that the only possible reaction for the bank, which is alive after the shock but below 8% for the capital ratio, is to sell some assets. So by selling some assets, once again, it's going to make the denominator decrease, so the capital ratio is going to increase back. Right? And so all the liquidations, so you look at the bank at day t, shock occurs at day t plus, so just after you looked, and all liquidations occur at day t plus 1. So by convention, in our setting, if a bank is unable to restore its capital ratio above 8%, it means that it's not complying with the capital requirement from the regulator. So in our setting, we assume that it's liquidated, fully liquidated. Okay? So for each bank, we denote xi, the proportion of risky assets that is sold in reaction to the shock. Right? So if the shock is not large enough, is not large, too large, xi is equal to 0. So banks are not going to liquidate. If the shock is super large, xi is going to be 100% because the bank will be fully liquidated. But for intermediate shocks, so between delta sell and delta fail, xi will be 20% or 50% depending on the magnitude of the shock. Okay? So each bank is going to liquidate a certain portion of assets. And so actually the whole market is going to liquidate a certain sum of assets, right? So that can have an impact on the price of the assets. So here in our setting, we take, once again, the simplest form of price impact, which is a linear price impact. So we introduce this market depth, phi, which is a linear measure of the liquidity of this risky asset. And we say that if the total volume of the assets which are sold by the market is this sum here, so the sum of xj, qj, right? That's what is liquidated by the market. The impact on the asset is this sum divided by phi. Right? So it's a linear impact. So you see that, for example, if phi is infinite, so it means like perfectly liquid market, the impact is equal to 0. Okay? But for a finite phi, when you liquidate something which is of the order of magnitude of the market depth, right? So when you liquidate a lot compared to the liquidity of the risky asset, you're going to impact the price further. Okay? All right, so the strategy of the bank is to liquidate some assets in order to decrease the risk-weighted assets and increase the capital ratio back. But the problem is that other banks are doing the same thing at the same time. And they are actually going to make the price of the risky asset decrease also in the process. Okay? So the balance sheet of the banks can be seen like that. So after the shock, you have still the same quantity of cash, and here a lower value for the risky assets. And then you liquidate. And when you liquidate, you put what you sold in risky assets in cash, but the value at which you sold depends on what everyone did in the market. Right? The price that you get for selling the risky asset is actually dependent on what others have done in the market. Okay? So if you look at this balance sheet, right, you can compute the equity and the capital ratio. So the problem of each bank would be to make sure that the capital ratio after the liquidation process is above 8%, taking into account, factoring all the other banks' reactions. Okay. So we are in the setting of a game, right? So there's an equilibrium which is going to come on. But before going to the complicated part, very simple part is when the price impact is, when there is no price impact. So the market depth is infinite. Well, when the market depth is infinite, there is no strategic behavior here, right? Because whatever you liquidate in the market, you're not going to impact the price. So you can liquidate on your own and try to bring back your capital ratio above the 8%, right? So that's very easy, and we're going to see some formulas about the optimal strategy there. The complicated case is actually when phi is finite, so there is price impact, and your own liquidation strategy depends not only on the shock delta, but also on the liquidation strategies of others, right? So that's why we call that strategic. Okay. All right, so what we're going to look at here is at the best response of a bank given the reaction of all others and the shock. And we're going to look at the equilibrium, which would be the minimum that a bank would liquidate given what others do, right? Because we think that the optimal strategy for the bank should be to try to, of course, restore the capital ratio above 8%, but doing that by selling the minimum risky assets possible, right? So that they stay the biggest possible. Right? So if we look at that, we're looking at a set of Nash equilibrium, right? And for all initial shock delta, we can show that the set of Nash equilibrium for this problem, right? So the Nash equilibrium here are the optimal strategies of liquidation, is not empty. And there is actually one particular Nash equilibrium where all liquidations by all banks are the minimum. And we're going to focus on this one because it's the Nash equilibrium where all banks liquidate the least, which is good for them, good for all the banks, and also good for the regulator. Right? So we're going to focus on this one. All right, so in the case of no price impact, as I told you, it's easy to characterize everything. When delta is lower than delta cell, you don't liquidate anything. When delta is larger than delta fail, you liquidate everything. Right? But when delta is between, so the shock is in between, you have a certain strategy which actually depends on the capital structure of the bank itself. But you see, bank I's strategy, when there is no price impact, only depend on bank I's balance sheet and capital structure. Now, if we put some price impact, you see that bank I strategy is actually bank I strategy without price impact plus some correction terms, so at order 1 in liquidity. And if you look at the correction term here, it actually depends on what everyone else does. But what's interesting here is that we are able to track that, to express that explicitly, the reaction, the additional fire sales by each bank, depending on the capital structure of other banks. Right? And that's computed actually in those terms in red. Those terms in red are there only because there are market frictions, because there is not infinite liquidity. Right? All right, so let's focus now a little bit on empirical results. So we did that. We calibrated our model for the 30 banks which were used in the CCAR stress test. So that's the stress test implemented by the Fed in the US. So we looked at the 2015 stress test. So you can look at those banks, right? So you have the balance sheets which are given. You can calibrate the model. We'll see how we do that. Compute the Nash equilibrium, and look at the reaction in terms of price-mediated contagion of the market given a shock, right? So you can really stress test the market saying, okay, imagine that those banks had one common asset and you put a shock of 5% on that asset. How are they going to react in terms of fire sale? And then imagine that the price impact is this amount. What's the additional reaction in terms of fire sales? So that's the list of the big banks which we followed. So once again, there are 30 of them, but here I listed only the GSIB, so the systemic banks that we are studying. And the model is very easily it's very easy to calibrate it. So the alpha, once again, is going to be the risk-weighted assets divided by total assets minus cash, because it's what the aggregate risk weight that you would calculate, that you would use to calculate the risk-weighted assets, right? You can compute the delta sale and the delta fail from also the balance sheets of the information of each bank. And so, for example, here you see that the alpha for Citigroup is 70%. So it means that the average aggregate risk weight which was used by Citigroup to go from risky asset to risk-weighted assets would be 70%. Of course, Citigroup never uses 70%. It just uses several risk weights for several assets. But if we calibrate that into a one risky asset model, that would be 70%. So it's a real calibration here. Delta sale is 3.57. So it means that if the shock on risky assets of Citigroup is above 3.57%, Citigroup's risk-based capital ratio will be below 8%, and Citigroup will have to react. Delta fail is 8.98%, so it means that if the shock on risky assets is above this level, Citigroup will be wiped out. Okay? So we can look, for example, at graphs like this one. So here you have on the x-axis the size of the shock, delta, and on the y-axis the level in dollars of what is liquidated by the whole banking system in the US. So at least the 30 banks that we studied here. In blue, you have the case where the liquidity is infinite. So phi market depth is infinite. So you have, of course, something which is increasing. So that means that the larger the shock, the larger the volume of liquidations in the market. But you see that it's very convex, right? Because the larger the shock, not only the larger the volume that each bank liquidates, but also the larger the number of banks that engage in liquidations, right? So that's highly non-convex, right, in the beginning. Actually, you can show that it can be expressed as a difference of two call options. If you look at the other curves, that's for lower liquidity. So here it's a price impact of 1%, here a price impact of 3%, 5%, 15%. You see, of course, that the volume of liquidations is highly increased, and interestingly, it's increased for intermediate shocks, right? And this is computable in our assumption. So you can stress test the market not only through shocks, but also through various liquidities. Right? So I see Carol getting impatient, so I'm going to skip to the conclusion. So we can do a lot of stuff with this kind of model, right? It's very simple, but we believe it's intuitive and it takes into account the feedback which is generated by banks rebalancing. So it enables to quantify price-mediated contagion. One of the strengths, as I told you, is of this kind of approach is that it's very easy to calibrate them, right? So it's you can actually this can be done just on an Excel spreadsheet, right? You can just take the different Excel information of the balance sheet, which are published at every stress test, or which are available on the website of each bank, and then you compute that, right? So one of the consequences of that is that it can be useful to also kind of justify and refine some existing regulatory tools, which are such as countercyclical capital requirements or capital surcharges, right? So I'm going to end here. Thank you.
Thank you, Lakshithe. And are there any questions for one of the three speakers?
So it's for Lakshithe. So have you guys thought of any like dynamic problem like this with t plus 1, t plus 2, or like even continuous time?
Yeah, so that's a very good point. We haven't, but it would be very interesting to do that. Yeah.
Okay.
And one other, something else which would be interesting is that instead of looking at like a deterministic delta, putting some randomness there, and looking at the, you know, you put dynamics on P, the price, right? Mm-hmm. Plus, and you incorporate the feedback, and you look at what the resulting price dynamics would be, and this would go in your direction. Yeah.
Thank you.
Thank you. Any other questions? So maybe I should ask. Yeah.
Well, my question is to Uwe. Uwe, do you think, can you try to make this some implementation of these techniques so that you can really apply it to some problems in perhaps insurance or finance?
Yeah, that was the original aim and how we got funding for the project initially, that you can have it for variable annuities where customers have some choices to get capital or leave it with an insurance company, and customers don't use these options embedded in variable annuities as American options, so they don't exercise them fully rational. And so what kind of model should you take? And here maximizing expectations under distributional constraints gives an intermediate well-defined value as a reference strategy. And it's one possible choice to do it. I think one of the slides I skipped, I also had swing options in electricity markets, where you have to stay with the electricity consumption between certain boundaries. So that would be would give an entire set of probability measures, and you have to stay within that set of probability measures, not just one, but an entire set. Of course, then you would play the usual game of having some compactness assumptions there and apply the machinery. But you know, PhD students want to finish and go on. so often these problems lie dormant for some time.
Okay.
So that's for Uwe as well. And just a comment after what you just said about like the non-optimality, you know, insurance subscribers, like typically in those variable annuities. One just other way to treat it is to, for instance, assume that the rate at which like they will exercise, so it will not be optimal, is just unknown, but like, you know, will be between two bounds, like in the spirit of uncertain volatility model, you know, by for instance. And then you are just looking at the worst case for the insurance, for instance. But the worst case will not be the fully worst case, because we know that the insurance subscribers will not exercise optimally. So it's just be between those bounds. And then, then of course it rises. It leads to a nonlinear equation, but you can solve numerically by BSDs or the other. So that's just another possibility to treat this non-optimality.
Yeah, of course, that depends on how you choose the bounds.
Absolutely. Absolutely. And so
if you have that additional information, fine.
Absolutely. So either you look at how people, the insurance subscribers, like, behaved in the past, or even for the mortality case, actually, you can just, the mortality table, but you can take a cushion.
Yes.
And then, of course, all depends on the cushion. That's, basically
I thought
management decision.
I thought it would also be useful for cancellation of insurance contracts. So there is historical experience of how many people actually cancel the contract, and of course it's not fully rationally done in a fully rational way, but there is an influence on how much interest you can earn outside without using an insurance contract, and the financial market has an impact there.
Okay, thank you. Any more questions? Okay, so then let's thank the three speakers.